We'll wait for 2 to 3 minutes. Okay. Am I audible? Hello. Yes, am I audible?
Yes, sir, you are audible, sir. Good evening, sir.
Good evening. So, good evening, everyone. We'll start with the fifth session of the power quality course, and we'll continue with the previous week's problems on DSTATCOM, and eventually we'll move forward with some problems on your series compensators as well as UPUs. So I've planned like this, and for starting, if you faced any doubt in the solutions of the previous week assignments or have any kind of solution facing any issues, so you can just let me know. Otherwise, I will just move into the problems.
Sir, there was one doubt, sir. In the previous assignment, that is in week 4 assignment, there were questions about calculating the RMS current.
Okay.
So there we just calculated ISA, and for RMS, do we have to divide it by root 2 or no?
You calculated IS what? Peak or RMS? Then if it is peak, then it divide by √2.
Actually,
Get the
when we say
RMS.
415 volts supply, 415 is the RMS
RMS.
value.
Yes.
Okay.
Yes. So
Okay. So
whatever.
then
Yes, 415 when you say it is the RMS value. Inherently, when
value.
in any AC quantities that is the problems it is given without mentioning anything, you consider it to be the RMS value. And whatever you calculate using the RMS value is also an RMS quantity for AC calculations. So consider like that, and you don't need to divide in that case by anything. It will come like the RMS value only. If you want the peak value, then you have to multiply by √2 for sinusoidal signals. If it is asked nothing mentioned in the question, like, then it is implying to calculate the RMS value. If some questions also mention that calculate the RMS value, then also it is understood that you have to take the line voltage which is given. And obviously, when nothing is mentioned, this voltage is also the line voltage. Whenever I tell like this, that for example, in this question, 3-phase 3-wire DSTATCOM at 400 volts, it is implied that you understand when I mean by 3-wire, it is a star connected system. I don't mention that, but generally in power systems, when you hear of 3-phase systems, they are star connected for the line. And whatever voltage is given, this voltage is the RMS line to line voltage, that is 3-phase. And this is star, you have to assume like that. And since it is a 3-phase 3-wire system, it is understood that it does not have a neutral point. So the fourth wire is absent. There is you don't have a neutral wire. It has a neutral point, but don't carry the current in the neutral wire because the fourth wire is missing. So it is star connected, having a point. There is a juncture point, but the neutral wire is not there. So it is a 3-phase star connected system and employed at 400 volts line to line. That is RMS voltage. So like that you have to understand. So in these questions they don't specify, but you have to consider like that. Any other doubts you have in the solution or in the assignments, new assignments? Even if you don't understand something, you can just let me know. Before starting, I can clarify those doubts.
Doubt, sir. Okay, sir. Sir, we
Yes.
have got the KVA rating, 35 KVA rating, but answer is not coming equal to 35 KVA.
For which problem?
This itself.
This itself means?
No, this is not. Previous session, last problem, sir.
Previous session, last problem. Okay, one second.
Yes, yes.
So we calculated, right?
Yes, yes, but I am not getting that 35 KVA rating.
Okay, well, let the last question that we solved. Okay, I understood. So you just calculate the, that is, I think this was the question. So you can write here or you can just open the last session, right? So this was the problem, right?
Yes, sir.
Yes. So what are you getting in the
No,
after solving?
no, not this, sir. Same problem in which it is asked DSTATCOM KVA rating. Last example, I think.
Okay, this one. No, this is not 35. Did we calculate 35?
Yes, yes, this KVA rating. KVA rating. Here it is KVA rating. We have calculated 35 KVA rating.
36.
Yes, yes.
36.
Here it is on the top. 35 KVA, I think. But answer,
But it is
I am not getting this much of answer, sir.
No, how you are calculating, that is the question.
Okay, okay.
So you just tell me how you are approaching. Any steps you have doubt in or found it wrong in the calculation, you can just tell me. You are getting up to
Okay,
this?
okay. Yes, I am getting up to that.
This is coming, right?
Yes, yes. 35. Yes, yes, yes. 35
So,
kVs.
so now,
Okay. Somewhere
so
it
now
was
what
wrong.
you do? No. So now what you do?
Yes, yes.
You
Got
just do
sir.
like this: 230 into 51.96 into 3.
Okay, okay, sir.
So just check what it is coming. Then let me calculate once again. And again, if someone of you have doubt, let me mention. Whenever I write this as 230, this is the per phase RMS. Is the color visible? I will change the color. Black. So whenever I write, this per phase calculation, that is, it is a balanced system. So 3 times per phase power. I write like this.
Okay.
So then is because someone was having doubt in the RMS and peak. So when we do such per phase calculations, it is per phase RMS. And this is the RMS line current, which for star connected systems are nothing but RMS phase current. So you can get the 3 phase power. Just see how it is. 35.85. So actually, if you calculate, you will get 35.85, near about 36 kVA is coming. Okay.
Okay, okay, sir.
But don't forget to take the RMS values, not the peak values or the
Okay, sir.
what you can say. Don't take the peak values or the line to line. Take the per phase RMS values, not the peak or the line to line
Okay.
value. But
Thank
if
you.
you do like this for a balanced system, root 3 into V line to line into I line to line, that is also valid. All these two formulas are valid. But this formula is only valid when it is a balanced system. Remember. Also this formula, balanced. We are considering balanced, na? If the 3 phases are having different voltages, different currents, just sum them up. Take the per phase voltage into current, then next phase voltage into current, then third phase voltage into current, RMS values, and add them up. If they are not unity power factor, what you will do? VRMS into IRMS into cos phi. First one done. Then next one VRMS, IRMS, then the angle between them, another cos phi 2. Like that you can do. The 3 phase power you can calculate like that. So cos phi also is there. And these are all line to line RMS voltage. RMS line to line. Anyway, so don't make mistake. Everything you do correctly and last line you make the mistake, then the whole effort goes into vain, right? So while calculating, just use any of the two. Okay. Any doubt from previous week? Any problem you are facing doubt? I can just re-explain before starting the new problems, because these are the basics, right? You need to know this before moving on to the next, because those are advanced topics. So you need to have a better grasp over these fundamentals, how you draw the phasor diagram, what are the RMS values and peak values. So I can just explain and give some time if you need some explanation regarding some problems, because many problems we solved last week, right? Anything you tried and you could not do, you can just let me know. Yes, any concepts you need me to re-explain, or you are facing doubts in solving the numericals if you have tried some. Because someone was asking some doubts, I think, in the last week also. And just let me know if some concepts you need me to re-explain. Yes. Otherwise, I can move on. So shall I start or have some doubts? So no doubts, right? So I will start. Okay. So just read the problem, and it was a continuation to the last week only. We are solving some DSTATCOM problems. So more types of problems we'll look into, and then we'll eventually move on to the UPQC, right? And also series compensator, some problems related to phasor diagrams and advanced some topics we'll see, the numericals, right? So let's start with some basic problems, then gradually we'll advance. Okay. So now just read what it is asked, that in the first problem it is told 3-phase 3-wire DSTATCOM is there. So shunt compensator they are using, and it is deployed at 400 volts 50 hertz. So the supply is having 400 volts 50 hertz, and it is used, what it is used for, it is used for providing load balancing and reactive power compensation for unity power operation and single phase application. And no, this is the single phase load which is connected, right, which is being given, and single phase load, and what it is rating, 54 kVA at 0.8 power factor lag. And the load is connected across two lines. Means what is the voltage that is applied across the load terminals? If I ask you, what will be the answer? VL. If I ask you what it
400.
is, V load. So it is equal to V
Oh,
line to line,
yes.
which is 400 volts. So this you have to understand, that rated condition is given in the problem, that if it is, what it is meaning this line, that if you connect 400 volts across the load, maybe any does not necessarily mean line or phase. If you apply 400 volts, then it will have 50. Then this what is this power factor? Anyone? What power factor is this? What it is indicating?
Inductive
What is
load.
correct? And what is this power factor? Supply side or load side?
Load side.
So what it is actually implying, that if you have some voltage across the load, which if I assume to be at zero phase, then the current will lag, that you can infer from here. And how much lag will be? Just this angle theta, where theta is nothing but cos inverse of 0.8. But this is only giving me information about the load side. So don't confuse about what is the supply side power factor, because supply side power factor is what after compensation? Unity, right? However, even if you compensate and make it appear to the supply lines that it is connected as a unity power factor load, the actual power factor of the load is 0.8 only, because load power factor never changes. You only provide compensation, make it appear to the supply side that it is a unity power factor load, like for example a resistive load, but nothing changes about the load. Load remains same. So why it is important? Because once you know this 0.8, someone was also asking the last week also how to calculate R and J. Sorry, R and X for a load. So this will help you calculate R and X. Because how? Because you know the voltage, you know the kVA rating. From that you can calculate what is the impedance. From these three informations, you draw the triangle and then you get the R and X. So this line is mentioned just to give you information about the load. So now when you know about the load, can you calculate DSTATCOM kVA rating? So what will be the approach? We solved such problems in the previous week, like. So what will be the approach? Anyone? Yes, just do with me. First, let me know what will be the approach. You know that it is providing load balancing. You know that it is providing reactive power compensation. That means you know that the after compensation, the supply side power factor is also unity. So you need the DSTATCOM KVA rating. So is one question I need to ask you: is the DSTATCOM injecting any active power?
Yes, it should.
And why do you
Oh no,
think so?
sorry, not active power, reactive power. Sorry.
Yes. So it is not meant for providing any active power, because here you are only doing load balancing, which is just reshuffling the virtually reshuffling the loads and making it appear to the lines as of equal loading. Just like we discussed, nothing is fed by the DSTATCOM. That is in terms of active power. In terms of reactive power, why it is needed? Because you have a lagging load for which you need reactive power. So DSTATCOM should do what? What is the role of DSTATCOM here? One is load balancing, that is reshuffling of the active power by the lines, and another role is for which you need the DSTATCOM currents is to inject the reactive power. So what can I ask? What is the maximum reactive power that it need to reach, that the DSTATCOM should inject such that you have unity power factor at supply side? So what should it be? What do you need to calculate? Just think and answer.
54 sine theta.
54
54
into
kilo kVA into sine theta.
54 10 to the power 3 into
Yes.
0.6.
Sine of, yeah.
Yes, it is 0.6. So what it is actually giving? It is giving me the reactive demand of the load, right? But what you need the DSTATCOM currents. That is, you know, active power of supply side should be equal to, or I can write active power from supply equal to active power load. Agreed or not? I can
Agreed,
write.
sir.
So by balancing this, what I can determine? I can determine IS, that is supply side current. And by knowing the reactive demand of the load, what I can get to know from that? I can know what is the. I can know both. I can know the load current also and the reactive component of the load current also. So now what you will do? I told you previous week also one thing that is always satisfied for such shunt connections, that if I draw the single line diagram, this is the supply, there is the PCC point where you have the load, and draw like this. So single line diagram is only valid for balanced systems. Just to show you, I am just drawing, but you will get the feel. For example, you have source current, you have load current, and you have some ID. So IS plus ID equal to IL. This will always be valid per phase, right? So now determine what is the IS. How will you calculate IS? Because in order to know DSTATCOM currents, or in other words, in order to know the DSTATCOM KVA rating, what you need? DSTATCOM voltage and DSTATCOM current. That will give you KVA rating, right? The amplitude you multiply, amplitude of the voltage, which is nothing but this at the shunt is 400. This is known. Now you need the DSTATCOM current. In order to know the DSTATCOM current, you need to know the DSTATCOM current from these two data, source and load, right? Hello.
Yes, sir. Yes, sir.
So you just calculate the source current, right? How will you calculate the source current? Source is running at unity power factor. So the source will be responsible for feeding the power to the load. So you do like this. You can write like this. So just note that the load is balanced after compensation, right? So, and also the supply side power factor is unity. So they're asking you that after compensation, you just tell the DSTATCOM current rating. So the DSTATCOM current we need to calculate. Before that, the supply side current we need to calculate. So it will be 54 into 10 to the power 3 into 0.8 divided by 3. This is the per phase power divided by 400 by root 3, like we did in previous week also, right? Just calculate what it is coming.
62.3 amps.
Divided by 400 by root 3. $62.35 it is coming, right? Correct. This is the supply currents, right? 62.35 angle 0, 62.35 angle minus 120 degree, and 62.35 and angle minus 240 degrees. Now you calculate the load current, because load is also balanced. So load, you know what? That it is connected across the two lines, which is 400 angle. What will be the angle?
We'll assume 0.
No. You cannot
No,
assume 0.
okay. The load angle.
I explained also previous week that if VA is angle 0, you mean that VA per phase. So VB is at an angle minus 120, and again minus 120 is VC, right? So if you find VAB, what it will be? 30 degrees leading. So 400 angle 30 degree. This was the voltage applied across the load. So load current, if I need, this was the source, right? ISA. So what is this? ILA equal to minus ILB. Because if you have the load connected like this, where it is VAB, then if some load is connected between these 2 points, and the remaining third line is not connected, no load current in that point. So this is like this ISA, ISB will be return path. So ISA equal to ISB. Or if is ISB you sense like this, by general convention we take like this. So then ISB is minus ISB. So which is ISB is minus ISA. So because we show like this, like for example, you have 3 lines. We like write like this: ILA, ILB, ILC. That load is drawing some current. Some loads are there. Using that convention, this current is opposite to that. So ISB is ILB, not ISB. They're all load currents. So if I write what is ILB, ILB is minus ILA. So this is ILA only. ILA came and returned via this point. So this is ILA, this is return of ILA. And what will be ILB using this direction? It is minus ILA. So what is this current? 400 at an angle 30 degree divided by this load impedance. Load impedance you need to calculate. So what is load impedance? How we will calculate ZL? It is nothing but V square by S. What is S? 54. And what is the angle? Angle also you don't need actually, because you need the angle to calculate ZL angle. V square by S is mod of ZL, agreed. And S value you know, 54 kVA. And what is this? Line to line or face to face? What is this voltage? To calculate ZL?
Face to face.
Correct. Well, line to line only. So this is 400. So how will you calculate ZL mod? You can calculate. How will you calculate the angle? Just think. Yes.
2.96 Z.
No, that
ZL.
yes, that is mod of Z, right? Let me do one. 200 square divided by 54 kVA, right? 2.96, correct. But that is only the mod of ZL. How will you calculate angle? I told you. Load information given here. Just see this. Or I can mark with red color. Just look at this. All the load information given here. You have been given 0.8 power factor lagging load. Someone was also asking how to calculate R and X for load. ZL magnitude you calculated. How will you calculate angle?
Cos inverse of 0.8.
Yes, plus or minus cos inverse 0.8. How will you determine that? It is given as
Lagging.
lagging. So what will be angle, positive angle or negative angle of inductive impedance?
Negative.
No, positive, because V by I is lagging V. So any angle V and any angle I, theta V, you write. What happens in inductive load? I lags V. So this angle when it comes above, it is Z angle, theta V minus theta I. Theta I is more or theta V is more? In this situation, voltage and current lags voltage, whose phase is more?
Theta.
No. If I have some reference and I see anti-clockwise, this is theta V, this is theta I. So theta V minus theta I is positive always, because angle is lagging the current. Current is lagging the voltage, right? So the angle of the current is always smaller and the angle of the voltage is much bigger. So that's why the Z is having positive, and that's why you see some R plus JX for lagging loads, because the current was lagging the voltage. When voltage by current you do, that plus J will come using complex number. So plus cos inverse 0.8, which is nothing but around 36 degrees. So answer is 2.96, 36.86. I hope this much ohms. This is the ZL value. Now you know ZL. What you do? You plug it in here to find out IL. So what you will do? 400 angle 30 degree voltage applied across load whose impedance is 2.96 angle 36.86. What is the value coming? Calculate.
-135.1 angle 6.96.
135.1
13.
angle 6.86 with a minus sign, right?
Yes, sir.
Because so I can write here ILA is 135 angle minus 6.86 degrees, and here
Abhi,
I minus 135 angle minus 6.86. I can write like this. Is it visible?
Yes, sir, it's visible.
So ILB is also calculated, ILA is also calculated, because load will continue to draw whatever it was drawing, because nodes are not changed. The supply currents will be balanced, load current will be as it is, and it will be made possible by the DSTATCOM action. So ILC is what?
zero.
0. So now if I ask you what is IDA, IDB, IDC, that is the DSTATCOM currents, how will you calculate? Using Kirchhoff's current rule, you will apply like this, na? This is the load, this is the supply, this is the DSTATCOM. So IS equal to, or IS plus ID equal to IL. Now what is ID? ILA minus ISA. What is IDB or DSTATCOM? For that I use D symbol minus ISB. And what will be IDC? ILC minus ISC. So when you calculate this, you will observe some interesting points, which I will make you note actually. So just calculate what it is coming. Then we will come to see something important, which we will have to remember. So just calculate. and let me know the values. This part is important because you will see something important. To calculate what is IDA, when calculating IDA, you just subtract from ILA, this is ILA, and subtract it with ISA, which is this. When you calculate IDB, you just use this ILB, then minus this. And when you calculate ILC, use this minus this. Calculate what it is coming.
ISA is 73.47 angle minus 12.67.
No, IDA.
Yeah, sorry, IDA. IDA is 73.47 angle minus 12.67.
Okay. Then IDB. Is approximate, right?
Sir, this IDA is exact answer is 72.78.
Okay. It is more or less.
But angle is not coming, sir, like this, minus 12.
But I am getting this angle only. Just check. What are you doing? What two phasors are you taking? You tell me. Just apply in scientific.
ILE minus ISC.
IL?
ILA minus ISC.
Why ISC?
Then, achha, where to take ISC, na? Okay.
No, IDA is ILA minus ISA.
ISC, okay.
You
Okay.
do phase by phase to phase do. Now next current, what it is coming? So I can write. I have it with me. And 62.35 angle minus 60 degree. You can just note down. So one observation,
Sir,
anyone?
first angle is 73 at an angle of minus 6.86, na? This angle?
No, no.
Because, sir, ISC is 62.35 at an angle 0 degree, understand?
Correct. Yeah, so what? When you have some phasors having 0 degree and you subtract with 135 angle minus 6.87 degree, how will it look like? How will 135 angle minus 6.87 look like? Like this. You subtract it with some 0 degree phasor. So it will go this side. And then you add the two. Angle will be more negative.
Okay,
Correct.
okay.
That is correct. You just just see the addition of two complex numbers or the polar addition using the calculator, or you can just solve manually. First try in hand, then you do. So now, important observation.
Sir, one doubt, sir. This IDC, how did you get angle as minus 60?
What are you getting? Minus 240 you are getting, right?
Yeah.
You are getting minus 240, right?
Minus 240 is the IS angle.
Correct. Then what you see that when we are calculating, ILC was 0.
Yes.
Because your was connected between A and B points.
Correct. Correct.
So when you do ILC minus ISC, this only pops up as the DSTATCOM current. Agreed or not?
Agreed, sir. I'm not getting this value of minus 240. I didn't understand how it became minus 60.
Yes. But what is coming? Sorry, it will be plus 60, I think, right? 360 minus 240. Yes, it is with, I think. Yes, it will be minus 240 only then. Or
Yeah,
something like
minus 240
120.
only. Yes, yes. I was confused with that. Yeah.
No, correct.
Okay. Okay, sir.
So, any observation? So this is wrong, right? Will be minus 240 degrees. Any observation, anyone? Is the DSTATCOM injecting only reactive power or not? Screen has been frozen. 1 second. Just off and then present again. So is DSTATCOM only pushing active power? Only pushing reactive power? By seeing these currents?
Sir, screen is not visible.
Something.
Screen is not
Yes,
visible.
I just started present. Okay. Yes. Visible?
No, you are visible, sir. Okay. Now is visible.
So what I was telling, only the DSTATCOM, what do you think? By seeing these currents, just tell me what it is inferring that only is the DSTATCOM injecting reactive power, as we just discussed at the starting, that since it's only power factor correction, it will only inject reactive power, and load balancing, it will just adjust itself. So, but we see that the DSTATCOM is also pushing active power. Why is it happening so? Anyone? Just understand the basics, right? What you are having is, you are having like this AC mains, and load was connected like this, only between two phases, and this was the DSTATCOM. So who will carry this current in order to balance? The DSTATCOM is bearing this current, right? In order to provide load balancing. Some amount of active power this current has. That means that DSTATCOM will not operate only to provide reactive power, but it also has to support with some active power in order to maintain load balancing criteria. Using some control techniques, you will do load balancing such that the three currents are balanced. So one question I have, is this DC link self-supported, or you need some active power source at the DC link? If someone asks you in the exam, is it a self-supported operation of the DSTATCOM, or some active source you need at the DC bus?
Active source is needed.
Yes. So that's the main catch of this problem, that you have a single phase load connected here, which makes the load current 0 without any compensation, if you see. And once you connect the DSTATCOM, it has to push the 1/3 of the power this phase. For that, it needs some active power support. Carry this current, some batteries or something. So you understood, right? So that was the main purpose of taking this problem. So I hope you. That's why we do it so much hard work in calculating individually the load currents as well as the source currents. Otherwise, I could have only taken the reactive component of the load current and injected it with the DSTATCOM. I took the load just as we discussed at the very beginning. Hope you remember that this we discussed 54 into 0.6 into 10 to the power 3. Divide it with 400 and inject it with the DSTATCOM. So that is not possible here because the DSTATCOM has to carry both active and reactive component in order to provide both these features, that is load balancing as well as power factor compensation. Understood, na? So just practice these kind of problems for DSTATCOM, right? Next problem you just see. Next problem is easy because
So one doubt, sir. In this previous, in this question which we just solved, you mean to say DSTATCOM has to have this active power support only because it is actually generating an active power,
correct.
and that is
Because
specifically for load balancing only.
correct, exactly. Because if it
Okay.
is, because you see, if it was for not for load balancing, na, then the
Hmm.
DSTATCOM not have to carry that third current. No needed because there no
Okay.
need of supporting the reactive power when no load is connected. So in that
Yes.
case, the DSTATCOM currents would have been unbalanced, as you can understand. No
Yes.
problem of DSTATCOM currents becoming unbalanced. But what my point was that if your DSTATCOM is used only for injecting reactive power, then but how you decide it is actually like this. When the DSTATCOM is like an inverter, right? So it is a voltage source converter, and you have some DC link. So when you inject some active power, that DC link voltage is, if it is not self-supported, then it is okay because someone will maintain this DC link. But if it is self-supported, then the power has to come from the grid or from the supply to maintain this DC link voltage. In that case, active power support from the DSTATCOM is not expected. DSTATCOM alone cannot support the active power, that is, cannot provide active power. It only takes small amount of active power to maintain this voltage and support the reactive power operation. That is, it can support with reactive power operation to the supply, but not active power. In order to push active power, someone has to inject active power. Otherwise, where from it will supply the active power? Otherwise, the supply will have to provide. So in such self-supported case, because it cannot take the active power from the supply because load is not there. However, you want the load balancing. In that case, you are demanding active power from the DSTATCOM. So in such cases, it is not possible. It would have been possible if it was only reactive power compensation. Then self-supported DSTATCOM, you just connect, it will work. But not in this case. So there are some constraints which you need to understand. Not that you connect DSTATCOM and you will get everything. You need to have some topological adjustments also in order to arrive at some functionalities that you want or some features that you want. So control will not always give you whatever you want. I hope you get what I mean.
Understood, sir. Only doubt is the source of this active power in this DC link. Where exactly you mentioned batteries? So, is it in the
That
control system of DSTATCOM? You have some source, or is it like in the primary of the?
control is only signal conditioning. But
Okay,
talking about actually there is a source sitting there. What you will control? You will control the DC link voltage.
okay.
What means by that? That the charge coming into the capacitor should
Hmm.
be equal to the charge coming out of the capacitor. Then only the
Mm-hmm.
voltage.
Yes, remains constant. Huh?
So if someone is demanding the DSTATCOM to throw some active power, which is like in this
Mm.
case, then the DSTATCOM will
Okay.
throw the power. Then this voltage
Mm-hmm.
will go down. Then the someone will
Okay.
come feed some power into the DC link.
Okay.
Just assume a
Okay.
battery connected with the DC link in parallel.
Mm-hmm.
For such cases,
Okay.
we also need the capacitor also. The battery is sufficient. No capacitor is needed. But there is a capacitor always in order to for the IGBT switches to operate, and you have some capacitors there inside the inverter. So that is how mandatorily
Okay.
we need active power injection to maintain the DC link voltage, because supply
Okay, sir.
cannot DC link voltage, right? In that case,
Mhm.
there is no load balancing.
Okay, sir. Fine.
So
Understood, sir. Thank you. Thank you.
Sir, what is the answer, sir, now? KVA rating?
KVI rating, yes, correct. So answer is you just multiply what is the voltage that your DSTATCOM has, 400 volts. But is it line to line or phase to phase?
Line to line.
So you divide by √3. This per phase voltage, what I told you, you just multiply per phase voltage with per phase current. And since it is KVA rating, you don't need the angle between the two, voltage and current. You just multiply the mod of the voltage into mod of the current. You understood this, right? So mod of the
Yes,
voltage
yes.
into mod of the current. First one we did. Second one, mod of the current of the DSTATCOM. Sorry, what is the DSTATCOM current? 73. Mod of the voltage across the DSTATCOM into mod of the current applied by the DSTATCOM. So 73. Plus again you do 400 by √3. So you can take 400 by √3 common, right? Because voltage will be anyway same. Only the currents are different. So I will write it afresh. So writing with some other colors. The answer wise. So KVA equal to your, what is the voltage? 400 by √3. And then of the currents. What are the currents? Sum of the mode of the currents, right? So 60, what is it? 73, right? 73 plus 124 plus 62.35. Just tell me the answer.
Sir, shouldn't it be minus 62.35?
Why? I'm
Uh,
taking the mod. Current is minus something. AC current,
okay.
which is
Okay.
minus
Okay.
that current has a phase shift of 180 degree. Doesn't matter. DSTATCOM has to
Okay.
cut that current. So take the
Okay.
amplitude while calculating the KVA rating. Just
Okay. Okay, sir.
take the mods. If someone asks you what is the kilowatt rating, you just take the mods and the angle between those two mods. That is voltage mod into current mod into cos of angle between that mod. So it gives you the per phase power. You do it for one phase. For first phase, you do 60. What is it? 400 by √3. That is mod of voltage of one phase into 73 into, because this is per phase, so you need to do 400 by √3 per phase voltage into your 73 into cos of minus 12.67. First phase power is calculated. How will calculate next phase power? Next phase power is 400 by √3 again, same voltage. 124 is the amplitude of the current into cos of angle between those two. What is the cos of angle between the first voltage and, because voltages are like this, right? V angle 0, V angle 120, V angle minus 120. Or like this, V angle minus 120, V angle plus 120. Phase voltages are like this. So one phase voltage into this current. Kilowatt rating I am telling. Kilowatt, if someone asks you. Then multiply this voltage mod into this current, cos of angle between these two. Again multiply this next voltage, next current into cos of angle between 120, that is minus 120 and 145. So it will be 145 minus 120. So plus 120. Hope you understand, right? And take the cos of that. So accordingly, you will get the kilowatt rating. But KVA rating is easy. KVA rating don't need to take any angle or nothing. Just take the mod of voltage, which I already took, and it is same. So phase voltage I calculated into phase current. Next phase voltage into phase current. Phase voltage into next phase current. So all the three phase currents of the DSTATCOM multiplied by their respective phase voltage. Take the mod and sum up, calculate, and what is the answer? 400 by,
60 approximately.
yes, yes.
60 kVA.
Okay. Just let me calculate. Yes, correct. Around 60 kVA, 59.89 kVA. Okay.
Yes, sir. Approximately 60.
Correct. So this is the answer. So this problem gave you a full-fledged idea that how the DSTATCOM currents you can calculate, what is the approach, and behind that you can calculate the, after that you can calculate KVA rating. So next problem is right. This is the star connected load, and the three loads are unequal, as you can see. Three-phase 4-wire like this, and you have like loads are connected between A to N, A, B, C. This is then B to N, this is N, and then C to N, and this is the AC supply. This is also star connected, right? Fourth wire also. These are the loads. So now you connect a 4-wire DSTATCOM. The shunt. 4 leg actually. It's 8 IGBT switches. Also PS. Why you connected? You wanted balanced unity power factor operation. Same like previous problem, but now the topology changed. It was 4-wire system. So calculate line RMS currents. So you know that you have the loads like this, whose values are given as ZA, ZB, and ZC. So can you calculate supply line RMS currents in a balanced condition? What will happen in a balanced condition, anyone? Active power will be, net active power of the load will be split among the three, and approach is E by 3 by 415 or whatever is the voltage by root 3. That will be RMS currents, and mod of that all the same RMS currents will be there, all the phases. Agree? Because that is a balanced condition. So P net, how will you calculate? The question is that you have the voltage, you know the that is the load impedances. So can you calculate the net power, active power? Easy, right? V square into Y. VA square into YA plus VB square into YB, like that. V square by R is the power, right? This is real part, I can say. Or writing like this. You do like this. You also can calculate anyways. V by Z also you can do. To calculate I, take real I. And then, so what is active power? Anyone? How to calculate active power from this situation?
Root 3 VI cos phi.
But here you don't know I. You have Z and V. So simple one method is calculate the load currents. And active power is RMS square into R. No, this is the RMS current, not the real current. It's the RMS current. And real part of load you take. So also you can write this as V square into conductance. Agreed or not? E RMS square by R we write, or VRMS square by R of load. So you calculate 1 by R is G. So here also you can determine what is G for all, because Z equal to R plus JX and Y equal to 1 by Z. When you do 1 by Z and you just resolve and write it in G plus JB form. If it is plus, it will not be plus. Note, it will be minus. So plus minus, minus plus. G minus plus JB is the conductance. So what is conductance? G. So you take 1 by Z and real part of that. So anyways you can do, it is a longer method. It is a shorter method. This one. Which one? This one. Because you already have been given voltage. VRMS you all know. What is the VRMS of one phase connected across this load? What is it? 415 by root 3. VRMS you know. Now you only need to calculate the conductance values. GA, GB and GC. So do 1 by Z and take the real part. Each one you tell me. And your net power will be VRMS square into G. A B plus G is the net power. Calculate what it is. So you have 415 by root 3, which is the per phase. This per phase RMS voltage. Huh? Per phase RMS voltage. Because you are doing per phase analysis. So per phase RMS voltage I determine 415 by root 3 whole square into conductances. Because I want to take the real part of the load. That is the load admittance, right?
बिट्टू केव्हा गेला बिट्टू केव्हा गेला म्हणून हे आणू का ग्रेड आणि फीज
Oh, your voice is audible, I think.
Oh, sorry, sir.
So you can just see what is it coming. Active power, you can just let me know. So active power will be anyways VRMS square into GA plus GB plus GC. Or you can write IRMS square into RA plus RB plus RC. Because IRMS is not same, so IRMS square A into RA plus IRMS square B into RB plus IRMS square C into RC. Why is IRMS not same? While calculating the load, IRMS is not same because the load is unbalanced. You need to determine the net power. In order to determine the net power, you will do I square R or V square by R. In both the cases, only the voltage is balanced. Current is different because the load impedances are different. And you need to do this calculation prior to the compensation, so that you can determine the net active power demand of the load. After that, you will provide the compensation by applying this technique. P net by 3 per phase split divided by per phase voltage. So balanced per phase RMS current will be determined. But during a calculation of the net active power, the voltage only is across per phase is same, the RMS voltage. However, the conductances are different. Since it is so, the currents per phase are also different before compensation. So during calculation of active power, net active power demand IRMS square into R per phase wise you need to do. What is R? This is R. So when you calculate, I will leave it to you because we have other problems to solve. So the active power will come to be 101,858 Y. So 118582 split by 3, and when you do by 415 by root 3, the currents will come out as, I will write the answer in blue. So IS balanced, this will be amplitude wise same for all the three phases, and its value will come out to be 16, around 16.49. So this you determine, and you will get up to this 11858 watts. Just calculate and let me know if you have some doubts in the calculation. Moving on to the next problem. So same, just take a screenshot of this problem. So this is the same problem. Only neutral current of the DSTATCOM RMS value is asked. As you know, I neutral is ISA for the DSTATCOM. So we can write like this. What will be DSTATCOM neutral current? Anyone? For a 3-phase 4-wire unbalanced system, DSTATCOM neutral current should be, in order for the supply neutral current to be 0, is called neutral current compensation. So this is our aim. We want this. However, it is not true for unbalanced loading scenario, because for an unbalanced loading scenario, your neutral current will be ISA plus ISB plus ISC. When ISA plus ISB plus ISC is not 0, you have some unbalance. For that, ISN is not equal to 0. When ISN is not equal to 0, without compensation, you have neutral current. Connected the DSTATCOM to neutralize this neutral current. So who will bear this neutral current? Who will carry? By applying Kirchhoff's current rule in the neutral wire, the neutral current was existing. Now what we wanted, the neutral current in the line, this was existing. We want to make it 0. So who should carry the neutral current? The DSTATCOM, such that in the line it does not flow, because it was appearing from here. The node I can draw like this. You can have better understanding. So what was happening? This was the supply. So your load was ILA, ILB, ILC, and all these three were summing up from here, carrying ISN or ISN, I can say. But these are also, we can tell ISA, ISB, ISC. As you can see, ISA plus ISB plus ISC is summing up at this node to form ISN. Now I don't want this ISN. I want the neutral current to be 0. So I connect the DSTATCOM 4th leg here, 4 legs, and this current will be appearing here, such that this current is 0 in the line. So it depends where you connect the DSTATCOM. If you don't want the current to appear here, you just connect it after this. So when it comes from the return path and the DSTATCOM is connected here, so while returning only, it will float here, such that it does not appear here. You got 0 at the supply side. So it depends where, at which point you connect the DSTATCOM, so that during returning, that current flows into the shunt path. So the supply side, you never connect the DSTATCOM. You connect the DSTATCOM at the load side, so that during the return path, the current gets a shunt path of the DSTATCOM and it can provide the compensation. Hope it is clear, right? So you understood up to this. So the problem asks to determine the RMS value of the current. So I told you, during unbalance, your neutral current has some non-zero value, which is equal to ISA plus ISB plus ISC. And due to that non-zero value, your DSTATCOM will carry that current to provide compensation. So neutral current of the DSTATCOM will be at the neutral current of the supply to provide compensation and make it 0. So this will be equal to this. So just sum up ISA plus ISB plus ISC RMS values, and you get the DSTATCOM RMS value. And it is easy. You have the loads given, which is 400 by root 3 per phase at an angle. So consider the angle. Don't just add it, because this angle matters, right? So 400 by root 3 angle 0 is the first voltage divided by only 10 ohm, so no angle. So this is ISA. ISB is what? 400 by root 3 at an angle minus 120 degree divided by 20. ISC is 400 by root 3 at an angle plus 120 degree or minus 240, whatever you take, divided by 20. You just calculate these three currents and sum them up. You will see the sum is not zero because they are unbalanced, unequal amount of loading, which will lead ISN to be ISA plus ISB plus ISC, which is non-zero. And the answer I can see. So you can calculate by, I can give the value because I have it with me. So mod, I can take the mod, and it is coming 11.547. If you calculate, you will get the same. So RMS value of neutral current you can write. This is the RMS value, right? RMS neutral current of DSTATCOM, because now the line does not have a neutral current because it is compensated by the DSTATCOM. However, DSTATCOM carries this amount of neutral current. So rating you can calculate from there. So coming to the next problem, it is same. We have solved like this. Just take if you want to solve, and I will write the answers, right? So DSTATCOM KVA rating will come out to be 67.168 kVA. It is similar to the second problem which we solved, or the first problem also. The first problem of today and this problem is same. Just different values we just put. And solve this problem. This is a new problem. Solve this. So just read the problem first. When you are done, you can tell me the approach, right? Because the approach of how you are thinking is important. Then only you can solve the problems. If you have solved this, then you will get a feeling of the how the compensation is being done and some power balance you can do and then check. I gave you a hint, just think in that direction. What it is asking. Any idea? Just anyone wants to comment something? If they have read the problem, if they have some understanding or they want to explain something, they're free to do. Because this session needs to be interactive. Because you need to tell your how you are thinking. Then I can, because some other approach may be there. So it's good that you think differently. So just feel free to discuss and then we'll solve. We'll solve all the problems. So don't worry about the time, but it is important that you give your views also. Just think and tell me what should be the approach in this case for this problem. If you have completed the reading, then you can just speak. What you understood from the problem? Anyone? No one is solving?
No, sir, not able to understand or get a picture of what
Okay,
is
okay.
actually required here.
Yes, yes. You just you finished reading. All of you finished reading the problem, or take some time and just see. So what the problem is saying, you have the three-phase delta connected squirrel cage induction generator as a supply side. So you may have AC mains of the supply, or may have some generator sitting there. So just like that, you have been given that 400 volts, 25 kilowatts, 50 hertz, 6-pole delta connected squirrel cage induction generator is sitting there as a supply. This whole line means like that. So don't get confused by such statements. They are just given to indicate that you have a supply sitting there. First line clear. Then next line is telling you that that induction generator, since it is a singly excited machine, as you may know, unlike the synchronous generators, which is a doubly excited machine, a singly excited machine needs some reactive power for the voltage buildup, because the generator needs to build up some voltage in order to supply to the loads. But it does not, or it cannot build up the voltage till it is supplied with some external means, some reactive power. Who will do that? Anyone? Who will supply the reactive power in this case to meet the excitation requirement of the induction generator? The DSTATCOM, right? Agreed? And
Yes,
in
sir.
this,
Yes.
you need to have some battery connected at the DC link, because initially the who will charge the DC link? How the DC link charges? The DC link charges to the body diodes of the voltage source converter IGBTs. But in this case, the inverter needs some DC link voltage at the starting. At the beginning, you need to have some, for the DSTATCOM to be functional. Please understand, for the DSTATCOM, which is nothing but a voltage source converter, to be functional and provide you all the features, you need to have some DC link voltage sitting there. The question is, when the machine is itself a singly excited machine, where it needs some external excitation to build up the voltage, you need to have someone who needs to charge the DC link. So who will do it? Some battery or some external active power source, which is sitting there and making the DSTATCOM operation functional for the first time, because the DSTATCOM has a major role here in order to excite the supply, which is nothing but the induction generator. The DSTATCOM needs to be functional from the first t equal to 0 point, so that the reactive power is continued to send and the induction generator is rotated by the prime mover and voltage builds up. So self-supported action is not here recommended. Some batteries is suggested. So like that, 10 kVAr at no load, the generator will take. That information is known to you. And at full load, obviously, then the voltage will dip. You need more reactive power to maintain the voltage. And hence it is given that 16 kVAr when the full load is given at unity power factor. These two information is given to you. Now the next line tells you that the DSTATCOM is used to meet the reactive power requirements to excite the induction generator. Now, obviously, it is given that it is given the RMS current, right? You need to calculate the RMS current of the DSTATCOM. So how will you do it? And also in the condition when 0.8 leading power factor load is connected. The load is also given, and the generator reactive power requirement is also given. And you need to calculate the rating of the DSTATCOM. Simple. You have information about what the generator needs from the DSTATCOM, and also you have the information how much load is connected. And both are 25 kilowatts load and 25 kilowatts supply. Only the reactive power is needed, both for the load. Because why you need reactive power for the load? Anyone? Because it is 0.8 leading power factor load. So the load will also itself draw some reactive power. And who else needs reactive power? The induction generator. So what the DSTATCOM is supposed to do? Feed necessary amount of Q to both the load and generator. So through proper control, we'll inject the load and the induction generator, fulfill their excitation requirements and the load reactive power burden. So sum it up, net reactive power that the DSTATCOM has to push needs to be calculated, because only the DSTATCOM is doing what? Is it pushing some active power? Anyone? Is DSTATCOM pushing some active power to the load?
No.
Because the induction generator is supposed to do so. Both are 25 kilowatts at full load. And only job of the DSTATCOM in that case is to feed the reactive power. Whatever reactive power is required, information is given already to you for the load as well as for the generator. Now you need to select that what is the reactive power that the induction generator will take to build up the voltage at full load. So is it given somewhere? Check. 2 kVR requirements are given. One at no load, one at full load. Which one you will take? Obviously at the full load, because load is 25 kilowatts. So just see like that. Okay. If I try to confuse you by giving 5 such reactive powers and make it, for example, 10 kilowatts, I may do it. I may make it 10 kilowatts and give you 5 data. You should be in a tabular form. You should be able to pick from that data, because I'm giving you the data, so you should be able to pick that for that particular load, or for example, that particular loading on the generator. For example, if it was 50 kilowatts and load was 10 kilowatts. So what was the loading on the generator in terms of percentage? 10 by 50. So it is 0.2 or 20% loading. So if I give you 5 data, 10%, 20%, 30%, 40%, 50%, and also 100% loading, it needs so and so reactive power. You should be able to pick what is the reactive power requirement at 20% loading and select that, and that is the reactive power that is your DSTATCOM has to provide the induction generator to build up rated voltage at that particular loading. Understood? So if I write Q DSTATCOM should be sum of two reactive powers. The role of DSTATCOM is to inject reactive power. So if your load takes reactive power, then it is plus. I told you at the very beginning in the week 1 and week 2 also, source is built to supply and load is there to absorb. If source is supplying active power, then it is positive. If source is supplying reactive power, then also it is positive. If load is absorbing active power, then it is positive. If load is absorbing reactive power, which is so for lagging loads, then it is positive. It's written like that as per a mathematical convention, and we do it for a reason to confer from that whether the load is reactive or active. So for example, you see that load draws. For example, if I ask you that load draws minus 10 kilowatt of active power, what can you comment about the nature of the load? Anyone? Load draws minus 10 kVAR, kilovolt ampere reactive of reactive power. Then inherently I am telling that load is supplying some reactive power. So what kind of load is it is? Lagging or leading? Inductive dominated or capacitive dominated?
Capacitive.
Correct. So it is given in the problem that 0.8 leading power factor full load is given that the load is leading. It is leading means that the load is supplying reactive power. So what you will write here in the power balance? Power balance means I am just balancing the amount of reactive powers that the DSTATCOM has to provide. We know DSTATCOM has to provide both to the source and to the load. So what is Q load? I can write. What shall I write here? Some minus, right? minus over, you have the 25 kilowatts. So 25 kilowatts by point, what I can write? From power I can go to from this, right? This is 25. You need what? You need this. This is cos inverse 0.8. So just calculate this. X by 25 equal to tan theta. Theta is cos inverse 0.8. Calculate X. 5 into tan of cos inverse 0.8, right? 18.75. What I should write? The load is supplying this amount of reactive power. So supplying load means negative. And what is the source taking? Source is also taking some reactive power. Correct? Hello? Is it clear or not?
So this x by 25 is equal to tan of cos inverse of 0.8. I'm just trying to figure out how you got it.
Yes, just see. Is the triangle. And 0.8 power factor of the load is given. So I know the load power is 25 kilowatts. So power means this P, Q, and S. Load power factor is 0.3, means cos of theta is 0.3. Is theta. So if I want this Q, you know, Q by P is tan theta, I can write. Theta is what? Cos inverse 0.8 from here. So plug it in.
Okay, sir. Got it.
Multiply with, then you get from here Q value. So for DSTATCOM, it is supplying to the source and to the load. But load is feeding power to the DSTATCOM. That's why it is negative, reactive power. But DSTATCOM as a source should feed the reactive power, not take the reactive power. That's why we have plugged in negative. Another part, it is feeding to whom? The inverter. Consider during writing this line or power balance, consider DSTATCOM as a source. So if the DSTATCOM is supplying reactive power, you just plug it positive. If the DSTATCOM is receiving reactive power from somewhere, you just do negative. Because what is the main aim? No reactive power should flow to the supply. So whatever reactive power is building up from the load, it should come up to the DSTATCOM. So, and some portion of the reactive power obviously should go to meet the excitation requirement of the induction generator. So you will not get unity power factor completely at the supply side, because here you have the induction generator sitting. But obviously, this amount of power is additionally received from the load. The DSTATCOM don't have to do much work because the load is capacitive. Already it is supplying some amount of reactive power. But since the DSTATCOM is receiving it, we denoted it with minus sign. So now you can calculate Q DSTATCOM that it has to. Now key DSTATCOM is coming 2.75, means DSTATCOM should absorb 2.75. Because you can see from here. So since the load is too capacitive, it is meeting the excitation requirement of the induction generator as well as dumping some additional reactive power to the DSTATCOM. DSTATCOM is not allowed to supply, but it is absorbing some reactive power. So that here the DSTATCOM is behaving as a inductor if you consider it as a load. Hope this is clear. And if it is a source, that's why it is minus. we consider the DSTATCOM as a source. So it depends upon you that what you will consider. You want to consider the DSTATCOM as a source of reactive power, or you want to consider the DSTATCOM as a load of reactive or a sink of reactive power. Since in the starting of the problem we considered like that we will consider the DSTATCOM to be a source of reactive power. That's why when the load was dumping some reactive power, we considered that to be negative, since the source cannot absorb anything. So that's why negative. And the source, but the DSTATCOM has to feed, it should be positive because the DSTATCOM has to supply. That's why we do positive. Yet we saw that it should absorb reactive power. Since it is a source, it cannot absorb. That's why negative sign. Philosophies differ. So whatever your philosophies are, you can go ahead with the convention, but don't change the sign. Once you select some convention, don't change the sign midway. Go ahead with that. So the KVA rating you can get from here to minus 2.75, because rating does not have any sense of minus or plus. Whatever is your assumption, the sign does not matter. But its interpretation is important. What its interpretation is. So for that, you can just see this is the value that is coming. So from here, can you calculate the current, RMS current that is asked in the problem? You have the Q, which is only the role of the DSTATCOM to push the Q or to take the Q. In this case, it is absorbing reactive power, the surplus. So from this amount of reactive power has to be taken by the DSTATCOM. So its rating should be this KVA rating. Okay, so now you calculate the current from this. What is the voltage? 400, line to line. Now, can you calculate the rating? Sorry, the current, RMS current? So, you do reactive power by √3 into line to line voltage. Or you can do Q by 3 by V by √3. Any way you can do. And it gives you the currents. So, what it is kind QD, ID, okay, ID. So, what is ID coming? Do it. Q is 2.75 kVA, means 2750 by √3 into 400 volts. Is coming out to be 3.96. Everyone getting? I hope this is clear.
Yes, sir. Getting it.
3.96
Sir, yes, sir.
ampere.
Sir, could you draw a picture of how this is actually connected?
Correct.
This.
Correct. It is connected like this. I will draw. Because that is more important. So here is your induction machine, which is sitting here. This is the stator. Okay. And you have the coils and the squirrel cage, right? It is. So the rotor here. And you have the three-phase supply, right? So phase A, phase B, phase C. It may be multiple such windings, which is actually true, distributed windings, but we are drawing only the phases, concentrated. But it is not so for actual machines, it is distributed. So you have the three-phase supply, and it obviously needs some reactive power excitation requirement. So we connected the DSTATCOM as a source of reactive power. You may have seen papers where we can connect capacitor banks to provide constant amount of excitation. With some small voltage across those capacitors, we connect some capacitors such that initially they can push some reactive power, and we will rotate with prime mover, and then it will generate. Once it generates, you just connect with the load. First you generate the voltage at no load. Once it is done, then connect the breaker, and this is the load. The loads like this, which is 25 whatever given kilowatt at 0.8 power factor lead. Load can be anything. So this is the how the network looks like. Okay. So you try these two problems and let me know, right? So now coming to the series compensators, problems on series compensator, that is static synchronous compensators, and you can use also the shunt compensator we have seen, the DSTATCOM, or a dual version of the both, as you have already seen in the lectures, which is termed as power quality conditioners. So UPQC is, you must have seen in the lecture also, are of various types, where the UPQC is actually comprised of a series compensator, which is a dynamic voltage restorer, along with the shunt compensator, which is the DSTATCOM, which we have been solving so far. The shunt compensator is there like this. You can just see the just a basic network, how in a single line diagram I have drawn. Obviously, it is a 3-wire or a single phase. So as per application, you have many types of, as per control, you can, through this topology only, you can achieve many kinds of UPQCs. So, but the topology is this only, where you have on the left side a dynamic voltage restorer, which is a active series compensator, and you have the DSTATCOM, which is a shunt compensator. And the DSTATCOM provides features like your power factor correction, neutral current compensation, load balancing. But you have also seen that the DSTATCOM or the active shunt compensators are also used for zero voltage regulation. Then why we certainly added the series compensator? First, tell me the answer of that. You have seen the lectures, I hope. You must have completed also the assignments. So why was the need for the series compensator when using the shunt compensator we could have attained zero voltage regulation, provided you have some source impedance sitting between the supply side and the load side? You must have solved those problems. If you had some source impedance sitting here, it was possible to inject shunt currents of leading nature to attain zero voltage regulation. I hope you are comfortable with this, because you know the phasor diagram, right? That you have the voltage, which is the supply voltage, and you had some drop here, for which you have some maybe sag here, voltage sag, but you wanted to maintain zero voltage. So what you did, you injected leading currents. So what it happened, you had some sag initially, voltage came here due to the sag of connection, some high loads, and you do, this is the injected current by the shunt compensator, which made the current, effective current, to be leading, and plus is, or you can do, this is the voltage, so V minus your current, this is the source current, so V minus is minus jxs. So you know leading currents can do zero voltage regulation. So voltage is more, you can see, you can increase voltage like this. So using shunt compensator with the help of this source impedance, it is possible to inject leading currents and make the overall supply current somewhat leading in nature, provide for the reactive drop here, and make the voltages at this load terminal equal in amplitude with that of the rated supply voltage. But why we don't prefer this? Anyone? Why the series compensator actually came here? Anyone? And why the concept of then UPQC actually, after that only the concept of UPQC came? So you see, it is not economical to inject large amount of, because when the source impedance values are very less, then large amount of currents needs to be there, such that this drop Is into Rs plus Is plus JIS into XS, these are already very small. And to provide the ZVR, zero voltage regulation, at high sag condition, when high voltage sag happens at the supply side, even then you want to maintain the load side PCC voltage equal to the rated amplitude, whatever you have. So in that condition, it is very difficult to maintain the voltage, because high amount of currents are required if you only want to install a DSTATCOM and attain those features of voltages. So DSTATCOMs are good to attain the current quality problems, but not economical, I can say, because it will be very large in size, because its current rating will have to be increased too much to provide such features of sag, or only sag, I can say, amplitude compensation. But what about the harmonics in the voltages? Cannot do anything. Even the DSTATCOM cannot mitigate any kind of harmonics or spikes or notches that may appear in the supply side voltage. Those will directly appear in the line voltage, or I can say at the load PCC. So DSTATCOM is unable to provide any voltage quality improvement features like that. So what we did is we connected a back-to-back converter, voltage source converter, which is very popular. And in order to minimize this voltage source converter, what it does, the left hand side I am telling, it just uses the feature of voltage compensation. So it senses the voltage and compares with the rated voltage, that is the actual reference what you want actually at the load side, and takes the difference of the two and injects that kind of voltage such that V supply plus V injected is equal to V load. So all kind of features you can have, and all kind of features, by what I mean is that by voltage quality features you can attain using this DVR, which is sitting here. And both obviously you need to provide power quality improvement. By power quality improvement, I mean that both current and voltage quality should be good. Even if the supply side is having abnormalities like sag, swell, voltage notches, voltage unbalance, all those can be taken care of by the series compensator. And what will the shunt compensator do? The shunt compensator will provide features like power factor correction, then your reactive power compensation, load balancing, all those features, neutral current compensation. So both, if it is so, then at the supply side also I can improve my current quality, and at the load side I can improve my voltage quality irrespective of the supply voltage abnormality and the load current irregularity. So that's why UPQC is very popular, and the combined effort we can actually say is beneficial to reduce the individual stress of the components, that is stress of the components or the ratings of the components that are installed there. So it is very important that at what point actually you connect the maybe the DSTATCOM and the series compensator. So as you might have also seen in the lecture that the DSTATCOM at the supply side and the series compensator at the load side, where you want the voltage regulation at the load point, that is in distribution networks, you want the load PCC to actually benefit from the voltage quality. That is, distribution systems are having high impedance at the lines because it is at the fag end actually of the power systems. So high resistance or feeder drops may be there. So that's why that sag and swell phenomena are very common. But at the load, you don't want such abnormalities. So you connect the series compensator in those conditions such that your load is so receiving good voltages. So this is good for such applications in the distribution network. So, and the transmission network must have seen that the opposite happens. So these kind of networks are built and are economical in particular applications, not all applications, because their relative positions may change. So you must have seen all those in the lecture. So for that, we just will using this concept that just remember two concepts while solving the numericals of the series compensators. What concept? That the DVR, actually I can say the UPQC, which is a combination of the series and shunt compensators. What it does, it injects with the help of its DVR branch at the left side, it injects voltages, maybe quadrature, which you call UPQC, maybe in phase, which you call UPQC P, or any angle, what you want, UPQC S. So variations are there, but the topology remains the same, only while they are control you inject such voltages. So generic is UPQCS, and you inject such voltages such that your load voltage is of a particular rated value. And with the help of the DSTATCOM, you have already seen, you have already solved the problem, so it is same. So main thing is we will target the series compensators and also solve the problem of sag and swell and all those things. So try the first problem. It is a basic static series synchronous compensator. So only it is like the series compensator only. No UPQC, no shunt is there. Only the series is there. So it is just a supply. It's 250 volt single phase supply, 50 hertz, and you have this device connected here. and this is a static device, and obviously it is connected in series, and it will provide some V. I can say this as VS, and I can say this as some V compensator. All these are AC quantities, so please denote by small letters. And your ZL is actually 7 plus J7. Okay. And what you want at this load terminal, also you want mod VL equal to mod VS. Clear problem?
Yes, sir.
Yes. And for example, assume you have some source impedance also. For which actually you need the voltage regulation at the load point. So in that case, what is the magnitude of voltage that you or the volt ampere rating it is asking you to calculate? So what is the basic idea behind this? Anyone? So you need to have control over the phasor diagrams for solving such problems. So by phasor diagram, what I mean, one thing you just know that this voltage you can assume as the reference voltage. Agreed or not? The supply voltage you can assume as the reference voltage. I think screen is frozen. I will just stop the presentation and then again start it. Just check if it is visible.
No, sir, it's not. Yes, the screen is coming up. The desktop is seen, sir. Yeah, okay. Desktop.
So one thing you just need to see while drawing the phasor diagram, because all these problems of series compensator, calculating the VA rating, you need to have a grip over the phasor diagram. So grip over the phasor diagram, for having it, you need to draw the phasor diagrams. For drawing the phasor diagrams, you need to assume some reference. So assume the supply voltage to be your reference. So draw it. So this is VS, whose magnitude is, this is VS RMS, okay? And it is given 30 at an angle 0, I can write. So these volts we can write later. So 230 at an angle 0. Now, how will your load current look like? IL is V S angle 0 by ZL angle something. So ZL you calculate what is the angle? Angle 45 degree I can see, because it is equal amplitude, and this is 7 root 2. 7 root 2 means it is something 9 point something, it will come 7 root 2. 9.89 it is coming. Angle 45 degrees. So 45 degrees I write, and ZL is 9.89 and voltage is 230. So current is something 230 by 9.89, and your angle is 23 angle minus 45. This is the IL. So how will IL look like? What is it mentioned in the question? Please read. So this voltage should be such that net loading on the system should appear to the supply as a unity power factor load. So if you would not have connected the series compensator, how was your load?
Lagging.
Correct. So my load was lagging, but it should not have been. It should not have been such, because the supply is now seeing that a lagging current is flowing. Because in such cases, in systems like this, your load current and source current are same. So without compensation, your load current and source currents both were lagging the supply voltage, which is making the supply see that it is a lagging load. But you don't want it. You want your load, effective load on the effective loading, I can say, on the supply, or you can say a fictitious loading on the supply can be like it is a unity power factor loading. Means that supply voltage and supply currents should be in phase. That is what you want. You don't have it till now, but you want to have it. Okay. So assuming you have attained so, they are asking you to calculate the volt ampere rating of the compensator. So assume that you have attained so by injecting proper voltage, which you don't know. But you know one thing, that your current should be in phase with the supply voltage, because this is mentioned that it is to be realized as a unity power factor load on the AC supply system. Please read the full term. It is not unity power factor load. Please don't confuse with the statement. The statement is telling unity power factor load appearing as a unity power factor load to the AC system. That is, to the supply, it is appearing as a unity power factor load. The load is not unity power factor. Load is having some reactive component with it, but it is appearing with this compensation that it is a unity power factor load. So your supply and load currents are, after compensation, they are both in line. That is in phase with the supply voltage. So I draw the phasor diagram like that. IS equal to IL. Up to this is clear, right?
Yes, sir.
Yes. After you tell me now, IS equal to IL you have attained, and both are in phase with the supply voltage. Now, if this current, if such current flows into the network, what will be your voltage across the load?
VS supply minus IS into ZS minus IS into.
You calculate that. But you know one thing, that load voltage is also compensated to equal value
Yeah.
by the compensator, which is equal to the supply. So that you know, and you also, why you to do so hard work, you know the current, you just multiply with the load impedance, you get the load voltage. IL into ZL is VL. Don't need to do VS minus IS into some, because this is a voltage. VS minus some del V by this compensator is obviously voltage, but easy way is this, IL into ZL. So IL, you tell me, IL is angle 0. What is angle of ZL? 45 degrees. So how will the VL look like? It is a circle, and VL will have equal amplitude of that as supply, and it will have phase of plus 45 degrees. Understood this point? Why it will have phase of plus 45 degrees? Because what is VL? VL is IL into ZL. What is phase of IL? IL phase 0, right? And ZL phase is 9.85 or 9.89 angle 45. So VL phase, whatever is IL, IL is determined by this term. This term is a regulating term. V across the, or V injected, I can tell, by the static series compensator. So this will regulate IL, but it will be so such that the voltage amplitude is 220, equal with the supply. That is the main aim. And if so, then the voltage will have angle of 45 degree. Understood this?
Yes,
Hello?
sir. Yes, sir. Yes.
So now if you have an angle of 45 degree, you know the voltage, you know the supply. Can't you calculate this injected voltage? Because you know KVL, Vs minus Vc equal to VL. So this difference. So you do Vs minus VL equal to Vc. Yes, you know. To you need the VA rating, right? So what is it coming? 230 angle 0 minus 230 angle 45 degree, right? So what was the rating? Voltage into current. Load current, you know. What is the magnitude of the load current? 220, which is the mode of the load voltage. And you have the impedance. Impedance is 7 plus J7. So 7 plus J7 is the amplitude of the load impedance, and then you 220 divided by 7 plus J7. You determine how much is the load current, because you need both the current and the voltage injected. Both multiplied will give you the KVA rating. So determine mode of this and calculate IL and calculate PC. So this is 220, not 220, it is 230. 230 by 9 point something, right? This is the load, this is the amplitude of the Z, mod ZL, right? So 230 by 9.89, what it is coming? 23 point
23.23.
20.2. So keep it in as the SI, as the current, and determine the voltage. 30 minus 230 angle 45, what it is coming? Some 176. Just calculate the amplitude, right? Sign does not matter. So around 176 volts will come. 176 multiplied by 23.2 is your KVA rating, or volt ampere rating is asked. Don't give in KVA. So 176 multiplied by 23.2. What it is coming? Some 4083 or 4083 or 4085, something like this. Volt ampere,
Yes,
right?
sir. Yes.
So this is the answer. Now you know that you have to use these informations, that your load voltage amplitude is equal to the supply voltage amplitude. You have to assume and then calculate. Such that you can calculate actually this injected voltage, because this is the actual unknown. Known parameters is what is given in the problem. Assume that and apply calculation, and then you just apply KVL and calculate the injected voltage amplitude. If you calculate injected voltage, you obviously know the current. How you know the current? You know the current from the information that load voltage is equal, amplitude is equal to the supply voltage amplitude divided by ZL to get the amplitude of the current. Amplitude of the current into amplitude of the injected voltage will give you the volt ampere rating. So that was the main aim. So the information of the amount, equal amount of voltage amplitudes, one thing you used, and what was another information you used in this problem is that the supply side what you have is having unity power factor. So these two conditions you used. Both are given in the problem. Apply those, and then accordingly you will get the injected voltage to attain such functionalities. That is the function of a series compensator. With this problem, I hope you got a basic understanding how the series compensator functions. You need these functionalities. Your control will tell what amount of voltage to inject, such that you get both these features. I hope this is clear, right? So virtual impedance, it is a virtual impedance which actually controls both the load current as well as the voltage. I hope it is clear, right? So we will stop today here, and UPQC problems, I hope next week we'll target, right, by Sunday. So more problems we have on UPQC and but basic understanding is like this, and I will suggest that you watch the lectures also. You will have a understanding of how the phasor diagrams are drawn, because all those angles beta and theta, what are they? So maybe you have to have a, I will tell you, but you will get more insights once we solve the problems. More problems you solve, the more clarity you will get, because we will take different kinds of problems, right? That's why it is better that you just see those lectures and understand the terminologies that are used and what are the conditions that are being used in solving this problem. So that will make you solve with me and you can just practice more. Okay, so we will just stop here, and if you have some doubts, you can let me know, right? Or you can just group calls if you have some doubts, right? So solutions till week 4, I think, have been posted, right? Someone was asking in the group also regarding the solutions.
Where exactly is it, sir?
Assignment where just check the portal, NPTEL portal, in the week solutions. There is a tab. Just click it and you will get it. Okay.
Okay.
So when is the week 5 due?
Next Wednesday, sir. I mean, coming Wednesday. That is 28th.
28th Wednesday. Okay. So you just, I hope we have discussed all the problems.
I didn't check, sir. I didn't check the kind of questions.
So just check and then I think it should be fine. Okay.
Okay, sir. Fine.
Okay.
Thank
so we'll
you,
stop
sir.
here. Thank you.
Thank you, sir.
So from next day, we'll have the session in Sunday only, right? Not
Okay,
next
sir.
tomorrow, but because
Yes,
we
sir.
prepone the session.
Yeah.
From next week, we'll have in Sunday only, right?
Okay,
As
sir.
usual, 5 to 7.
Okay, sir.
Okay. I'll give a
Thank you,
reminder
sir.
in the call. You'll
Okay,
get
sir.
the announcement in the portal. Okay.
Okay, sir. Thank you so much, sir.